Hi all. So in today's class we will continue with the module 1 and discuss in detail about the thyristors. We have already come across that there is a 4-layer device known as a thyristor in the history, and due to this device, that is a thyristor, a new electronic revolution came into existence, and that part of electronics is known as power electronics. So thyristor is nothing but it is a 4-layered device, and it is also known as a bistable device. Bistable means by two stable states, one is the off state and the other is the on state. And we also know that whenever we use a different semiconductor devices such as diodes and transistors, we came to know that in power electronics field we are going to use these semiconductor devices mainly for its switching action. Switching action means turning on and turning off. So here thyristor is a bistable device, stable states, two stable states. That is why we prefer a thyristor also. And thyristor, the word thyristor is derived from two different devices, that is thyristor is derived from two different devices, that is Thi is taken from the thyratron and ristor is taken from the transistors. So the combination of these two is nothing but the thyristor. Thyristor is a 4-layered device, 4-layered, that is PN 4-layered device, which is having 3 terminals, anode, cathode and a gate, and 3 junctions, J1, first junction J1, second NNP junction J2 and PNN junction J3. So thyristor is a 4-layered, 3-terminal, 3-junction device. Okay. Now as we see the structure PN, the similarity is like a PN device. A PN device is nothing but a diode, right. So let us go back to the functioning. In order to understand the working of the thyristor, let us understand how a simple diode works. Works means how it turns on and how it turns off. Okay. We know that in case of a diode, a PN junction device, there exists two states. One is the on state and the off state, or we also speak with respect to the biasing, forward bias and reverse bias. Now let us say that we are going to connect it to a battery supply. Okay. And we also know that in case of a P region, what is in excess? Holes are in excess. So we have holes in excess in a case of a P region. In case of N region, what happens? In case of N region, electrons are in excess. Okay. So now when we are going to connect a battery terminal across a P layer, the positive potential, across the N layer the negative potential, then what happens? Here we have a positive polarity and the positive polarity is reflected here. Positive and positive, we know from the basic law of energy that whenever we have like charges, it will repel, move away from each other. That is what is happening here. So when we are going to connect a positive potential, it is going to repel. That is, it is going to, the holes are going to go towards this layer because of the repulsion action. Similarly, coming to this part, N, excess of electrons are there in the N region and we have connected it to the negative potential of the battery. So negative and negative, again here it starts repelling. So once it is repelling, it goes away like this, moves away. So when this potential is applied across a PN junction diode, then what happens? Automatically this barrier, whatever is there, is broken down and it allows the current to flow through it, right. So what happens? When the current flows through the device, then we say that this device is in the on state. Followed? Now, on state, or we also speak with respect to the forward biased condition. So, we have already studied that the forward biased condition of a diode is when the junction is broken and the free electrons are flowing into the device and allows the flow of current, we say that the diode is in the forward biased condition. Similarly, when we say that the reverse bias condition of a diode. Now, when do we say reverse bias condition of a diode? So, here what happens in this case? Here change the potential of the battery. Instead of connecting the battery like this, now in this case what will happen? The negative potential of the battery is connected to the P layer. P layer, excess of holes are present. So, excess of holes are present in the P layer. So, what happens here? Negative, unlike charges attract each other. So, what happens? Here you have a negative potential, here you have a positive potential. So, it moves towards this. Okay. Similarly, the other side, here you have a positive potential. In case of an N region, electrons are in excess. So, unlike charges attract each other. So, what happens? It moves towards the potential. So, what happens here in between the junction, the gap thickens. Okay. Once this gap or the junction between a P and N region is wider, then there is no flow of current taking place here. If there is no flow of current, what happens? The device is said to be in its off state, or it is also known as the reverse biased condition, right. So, this is clear, forward bias condition and reverse bias condition. Here coming back to the thyristors also, PN almost similar to the working of a diode. So, the symbol also, if you see this part of the symbol, this is the symbol of a thyristor. So, anode, cathode, the representation is similar to that of a diode because it follows the same principle, working principle of a diode, except for the gate terminal. So, now let us see how this gate terminal plays a role in turning on the thyristor. Okay. Now, whatever the characteristics what we are going to study, how it is going to turn on and how it is going to turn off, that characteristic is known as the static anode cathode characteristics. So, under static anode cathode characteristics, we are going to see how these junctions are broken down. Junctions are broken down means this is what it is going to be in its on state. If junctions are not broken, the width of the depletion region keeps on increasing, then it is in the off state. Okay. So, now let us start the analysis for this 4-layer device under static anode cathode characteristics. Now, let us assume that anode and cathode. Now, for the time being, keep this gate aside. So, we will take anode and cathode. So, let us say that we are going to provide positive potential to the anode and negative potential to the cathode. Okay. So, during this condition, what happens? Positive, come back to this layer. In P region, we know holes are in excess. In case of N region, electrons are in excess. So, now we are applying the positive potential across the anode and we are going to apply the negative potential across the cathode. During this point, what happens? Like potential positive and like charges, that is holes are there, like charges repel each other. So, it will move away, it will move towards this point, breaking this junction J1 and it will make a pair with the free electrons available in the N region. So, in this case, when you apply the positive potential, J1 is forward biased. Okay, come back to J3 here, you are applying a negative potential here, electrons are in excess. So, what happens? Repulsion takes place because like poles, like charges are present here. So, this moves towards this side, breaking the junction J3. Once we say that the junction J3 is broken, then it is nothing but forward bias condition. What about J2? J2 is still in the reverse bias. Okay, this condition where if we say that forward bias condition, there is a small current flowing in the device. So, there is some small current here, there is some small current flowing here. So, this small current, when you are applying positive forward direction, forward bias condition, this small current is known as the forward leakage current. When junction J1 and J3 are forward bias, it is only a small current flowing. Why only small current? Because still this junction J2 is in the reverse bias condition and it is in the off state. Okay. So, this off state is also known as blocking state. Instead of mentioning it as off, we mention it as blocking state. Okay. Now, the gate comes into picture here. Now, we are going to apply, we have the gate terminal. So, gate to cathode, you are going to apply gate positive, cathode negative. This voltage is going to be applied here. What happens? Positive, positive, repulsion takes place. So, already negative is applied here. This extends the force and what happens? This junction J2 is in the forward biased condition. Now, what happened? Once this J2 is broken down, that instant of time when J2 is broken down is known as the forward blocking state. Okay, forward blocking state. After this instant of time, once the J2 is broken and forward, it enters forward biased condition, then from the anode to the cathode, there is a high flow of electrons. The current is very high. Okay, that during the current is very high, that is known as the on state. Okay, that is how the thyristor goes to the on state, from the blocking state, that is the off state, to the on state with these parameters, junctions forward biasing and the junction J2 getting into forward bias condition. Only when this occurs, the entire device allows the flow of current. This is the on state of a thyristor. Okay. So, what are the terms we came across? Forward leakage current, blocking state, forward blocking state and the sudden inrush of current, that is also known as the latching current. Latching current means IL, represented as IL. So, latching current means it is a minimum current, that is what is a minimum current that is required for the device to go to its on state. That minimum current, that is always the minimum current, means it is a, in terms of its values, it is a high value of current, that is known as the latching current. So, in order to turn on the thyristor, we require the latching current. Above this value, above the value of the latching current only, the device can be in its on state. Okay. Now, let us come back to the, we have studied how it is going to be in the on state. Now, let us see how it is going to go to its off state. When we say it is going to go to the off state, what we need to do? We need to reverse this terminal minus and plus, change the polarity. Across anode, now you are going to give a negative supply and across cathode you are going to apply the positive supply. So, what happens? Negative potential, holes are in excess. So, unlike charges attract each other. So, negative and positive, so it goes towards this. So, what happens to J1? J1, the gap, the junction gap increases. If the junction gap increases, what will happen now? J1 will be in its reverse biased condition. Okay. Similarly, coming here down, we are applying the cathode with a positive potential. So, negative N region, electrons are in excess. So, electrons plus the positive potential applied, unlike charges. So, here also attraction takes place. Electrons start moving towards the applied positive potential. This gap or the junction gap increases. If the junction gap increases, we know that it is a reverse bias condition. Now, again what happens? We have reverse bias means off state, but still this J2 is in the forward bias condition itself. So what will happen now? There will be some small leakage current due to J2, and that leakage current is known as the reverse leakage current. In the opposite direction, we will be having the reverse leakage current. Further, as we are going to increase the potential here, what happens? The excess of electrons and the holes, whatever we have supplied, in turn this J2 will also reach the reverse bias condition. Okay, that is here also the gap increases as we are going to pull the electrons and holes to the other side. So when all the three regions are in the reverse bias condition, it is said to be in the off state. Now when we are going to discuss about the off state of the thyristor, another current comes into picture, and that is known as the holding current. Holding current means that is a minimum current that is required for the device to be in the on state. After the holding current, it will go to the off state. That is at the point when this junction J2 goes to the reverse bias condition. After that, there will not be any current flowing to the device, that is a thyristor. Okay. So when the J2 goes back to the reverse bias condition, that minimum current, that is known as the holding current. Okay. So whenever we purchase a thyristor, we will have to know what is its latching current and what is its holding current, the specification. Okay. Depending on that, you can use this thyristor for the different application. Now you might have understood what is this bistable, how it is going to be in its on state and how it is going to go to its off state. With the same concept, we will draw the VI characteristic. Since we have understood the different regions of operation, the VI characteristics can be drawn as, let us say that we are going to plot a graph across the anode current and the anode to cathode voltage. So initially blocking state, forward blocking state, that is when we are applying this potential. When we are applying this positive and negative terminals here, this is the region of operation. So what happens? There is a small leakage current. Why is this leakage current? Because J1 is forward bias, J3 is forward bias, there is a small current flowing. Okay, that current is the leakage current. This is the leakage current, but still, whether we have the leakage current available, still the thyristor is in its off state. There is no current flowing from anode to cathode. So we say that this portion of the graph is nothing but the forward blocking mode. Right? So next, at one instant of time, which instant? When you are applying the gate voltage, gate to cathode voltage, at one instant of time, what happens? This J2 suddenly goes to the forward bias condition. At this instant, there will be a high inrush of current. So this forward breakover region. From this point, this is the point where the device goes from the off state to the on state. Okay, so that is known as the breakdown region, and suddenly what happened? Current rises to the maximum value. Now current rises to the maximum value, it is nothing but a PN device. We also know that in case of a diode, the on state voltage drop. What is the on state voltage drop of the diode? It is nothing but 0.7 volts. Means when the diode is in the on state, the voltage drops to 0.7 and the current increases because of the flow of electrons. Similarly, in this PN device, that is a thyristor also, when it is going from off state to on state, the voltage drops around 0.7 or 0.8 volts. Because it is the on state. When it is in the on state, there will be some voltage drop across the thyristor, but current increases. Okay, as you keep on injecting electrons into this 4-layer device, the electron starts moving and the current keeps on increasing. Look at the voltage, it is at the on state, so it is 0.7 only. Right? So 0.7 voltage, this part, that is when the thyristor is conducting in the forward direction, it is known as the forward conduction region. Okay. Now, when we are going to the reverse bias, next part is when anode is connected to negative and cathode is made positive. During this operation, what happens? There will be some reverse leakage current. Why is this reverse leakage current? J1 is reverse bias, J3 also reverse bias, but J2 is still in the forward bias condition. Hence, there will be a small current flowing in the reverse direction. So, that is known as the reverse leakage current. Once the reverse leakage current is there, what happens? Then suddenly at one instant of time, this J2 goes to the reverse bias condition. Okay. Now, when we are going to turn on, that is J1 forward bias and J3 forward bias, suddenly this J2 is going to break down. This sudden breakdown due to the high voltage applied is known as the avalanche breakdown. Okay. So, this is also reverse avalanche, forward avalanche, reverse avalanche. That is sudden breakdown of this junction J2 is known as the avalanche breakdown. So, this is how the characteristics of the thyristor lies, and always we have to note that this latching current will always be greater than the holding current. Okay. So, depending on this latching current, that latching current is when at the instant where you are going to turn on the device is the latching current. Holding current is you are reducing, you are removing the injected electrons from the device. Once you are removing the electrons, at one point what happens? This J2 goes to the reverse bias condition. Then what happens? There will be a minimum hold current. After this minimum current, it will go to its off state. This is known as the holding current. Hold the device in the on state is the holding current. Latch means we are using a latch to lock the door. If you open the latch, you can enter in. In the similar way, if you give the current, if you are going to give the gate current, above the latching current only it will turn on. Okay. Below the latching current, whatever you are going to do, it will not going to turn on. It is not going to turn on. Okay. So, latch, that is used as a latch. So, latching current for turning on and holding current for turning off. So, this is the basic operation of a thyristor in its on state and in its off state. Next, we will see about the two transistor model of a thyristor. Thyristor, previously we studied it as a diode, using the working of a diode. Now we will see how the thyristor can be divided into two transistors. One is the PNP transistor and the other is the NPN transistor. Now, when we take the cross sectional view of it, by cutting in the cross sectional view, we get this PNP and NPN type of transistor. That equivalent circuit looks like this. Now, here anode current flows to the PNP transistor. So, PNP emitter flows into it. So, emitter, collector and base. Similarly, here we are having a link between the base of the transistor 1 is linked to the collector of the transistor 2, and when you come here, the collector of transistor 1 is linked with the base of transistor 2. So, this is how back to back we are going to analyze the thyristor as a two transistor model by applying anode here, gate here and cathode here. Okay. Now, let us see in detail how the expression goes by making use of this two transistor analogy. Okay. Now, from the figure it is clear that this base current of transistor 1 is equal to the collector current of transistor 2. So, we can say that IB1 is equal to IC2. Similarly, this collector current whatever we are receiving here is equal to the base current of the second transistor. So, we can also say that IC1, this IC1 is equal to IB2. They are the same currents. Okay. Now, coming back here, anode current is flowing, let us assume G to be a node point. Anode current is flowing towards the node G and the gate current is also flowing towards the node G. But what about the cathode current? It is flowing away from this node point. So, applying the principle of KCL here, we are going to get that anode current plus gate current. This is the anode current, gate current, both are going towards this node, whereas the cathode current is flowing away from the node. So, the current flowing towards the node should be equal to the current flowing away from the node. So, we can take this equation as IK, cathode current is equal to anode current plus gate current. Call this as equation number 1. Okay. Similarly, using from the transistor analysis, we know that, use the same principle here. We know that the base of the transistor is towards one direction, whereas the collector current is towards the other direction. Both are flowing away from this point of the transistor, okay, whereas the emitter current is flowing towards the node point. So, if we have to write the equation, we will get, using the transistor analogy, IB1 is equal to IE1 minus IC1, or you can also write IB1 plus IC1 is equal to IE1. Okay. So, using these two, now we also know that by studying the basics of transistors, we know that we are going to include a small current gain in the transistor. So, we can also write the collector current IC as alpha 1 IE1 emitter current plus ICO1, that is the leakage current, reverse leakage current because of the reverse bias junction between the transistors. Okay. So, this equation also you are already familiar by making use of this transistor analogy. So, now making use of all these equations, let us substitute this IC1 in the above equation. So, substituting equation 3 in equation 2, what do we get? Instead of IC1, replace it by this equation. So, you will get IB1 is equal to IE1 as it is minus, instead of this IC1, add this alpha 1 into IE1 minus ICO1. Okay. So, now you can have the common factor here, IE1 is a common factor. So, take it outside, 1 minus alpha 1 is equal to ICO1. So, now we are also coming back here to this transistor analogy. The first transistor, the emitter current is same as that of the anode current. IE1 is nothing but the anode current that is flowing here. Okay. So, IA and IE1 are the same. We know that. So, substitute here, the equation changes as IB1 is equal to 1 minus alpha 1 into IA. Instead of mentioning it as emitter current, directly we are going to write it as anode current. Okay. Now, minus ICO1. Keep it as it is, call it as equation number 4. Similarly, we have two transistors. So, first transistor we have taken this equation. Similarly, applying the same principle for second transistor, we get IC2 is equal to, two transistors are there, two transistors will be having a different current gain. So, we have considering transistor T1 having a current gain as alpha 1 and transistor T2 having a current gain as alpha 2. Okay. So, alpha 2 into IE2 plus ICO2. Okay. So, now what we know that here, coming back to this figure here, we know that the PNP and NPN, this is an NPN transistor. So, emitter will flow away. So, this is the direction. IK, cathode current is same to that of the emitter current here in the second transistor. So, cathode current is same as the second emitter current flowing the transistor second. So, what happens now? Substitute the value, instead of IE, you substitute the value of IK. So, it will become as IC2 is equal to alpha 2 into IK plus ICO2, reverse leakage current due to the reverse bias junction. Okay. So, call this as equation number 5. Now, we also know that B1 is equal to C2, the base current flowing here is equal to the collector current of the second transistor. So, substituting this 4, 5 in equation 6. IB1, IC2 already you have found out, substitute in this equation 6. Now, what you are going to get? IB1 is nothing but 1 minus alpha 1 into substitute that equation. Now, equation 5 tells about IC2. Since both are equal, write the equations for the same. Now, take all the like terms one side. So, IA is here, IA, and here we have IA can also be replaced as IK, that is IK is nothing but IA plus IG. So, rewrite it IA plus IG instead of IK. Now, what will happen? IA terms you bring it one side, you will get 1 minus alpha 1 minus alpha 2. Directly I have taken minus outside, so alpha 1 plus alpha 2. The remaining terms you can write it on the other side. Since this reverse leakage current is very small, so IO1, ICO1 and ICO2 are negligible. So you can neglect it and you can finally write the equation for IA, anode current, as alpha 2 Ig divided by 1 minus of alpha 1 plus alpha 2. Now depending on this, you can see using this equation, when alpha 1 plus alpha 2, the current gains are, the value is equal to 1, what will happen? There will be an infinite anode current flowing in the circuit. So usually when using the alpha current gains, the anode current flowing in the device is usually a very high current. Okay. Now as we keep on reducing it, what will happen? We can take the values for the anode current flowing into the. So always alpha 1 plus alpha 2 must always be less than unity. Okay, otherwise you will get an infinite current. And the other way of turning on the device is when the Ig value, okay, if the Ig value or if the alpha to the current gain of the transistor is almost equal to 1, then what happens? Even in that case, the transistor can be turned on. So these are the different conditions that we speak about. By making use of this transistor analogy, we are going to find out the turning on of the thyristor, where anode current is nothing but only when the device is turned on there can be an anode current, and to get that anode current we have to vary either alpha 1 plus alpha 2 or alpha 2 can be varied. By varying this current gains from the transistor, we can say that this thyristor is in the on state by providing the sufficient anode current. So this is about the two transistor model. Thank you.